Hubble has been in space for over 34 years, and its mission has been an incredible success. Although it wasn't originally designed to observe objects within our solar system, it has managed to do so throughout its journey, capturing extraordinary moments that would have otherwise gone unnoticed. Not every planet has a dedicated mission, and there's much more to see in our solar system beyond just the planets. Let's embark on a journey through our cosmic neighborhood, venturing from Earth to the farthest reaches of the Solar System, exploring remarkable objects you might never have heard of as revealed by Hubble's keen eye. We will begin our grand tour close to home with our immediate neighbor, the Moon. Due to the Moon's large apparent size in our sky, Hubble cannot capture its entire surface in a single image. Moreover, other missions such as NASA's Lunar Reconnaissance Orbiter provide far better images of the Moon. Thus, Hubble's time is better utilized elsewhere. However, in 2012, Hubble captured an intriguing image during a special event, Venus passing in front of the Sun. Why observe the Moon during this event? Scientists used it as a massive mirror to detect subtle variations caused by sunlight scattering through Venus's atmosphere. These variations reveal details about the atmosphere's chemical composition. Although Venus's atmospheric composition is already well known, this experiment tested whether the light scattering method produces accurate results. Hubble frequently applies this technique to study exoplanet atmospheres by observing distant stars as planets transit in front of them. Since the Sun is too bright for Hubble to observe directly, using the Moon as a reflector enabled scientists to obtain the data they needed. While capturing the entirety of the Moon poses challenges for Hubble, the same is not true for Mars. Hubble often observes Mars, offering a full view of the planet, something orbiting spacecraft can't always achieve. These images provide valuable insights into dust storms, seasonal changes, and other weather phenomena. Such information is crucial for planning rover operations and building a comprehensive understanding of Martian weather for future predictions. In one time-lapse, a global dust storm envelopes the planet, obscuring surface features. Mars's two small moons, Phobos and Deimos, can be seen zipping around the planet in the background. Their rapid motion is especially noticeable in the 42-minute sequence. Another time-lapse focuses on Phobos, the largest and closer of Mars's moons, showing its movement over just 22 minutes. Phobos completes an orbit around Mars in only 7.5 hours, making it the only moon in the solar system to orbit faster than its planet's day. As we leave the inner planets behind and approach the first of the gas giants, we encounter the asteroid belt, a fascinating region filled with objects worth studying. Among them is the curious asteroid 6478 Gault, a misleadingly named celestial body that has captured Hubble's attention. You might be surprised to learn that this object, which clearly resembles a comet with its twin tails, is actually an asteroid known as Gault. This asteroid resides in the asteroid belt and was imaged in 2019. So why does it have a tail? Scientists believe the answer lies in a phenomenon called the YRP effect. Solar radiation exerts a small but steady force on irregularly shaped bodies, and under the right conditions, this can gradually increase their rotation speed. In Gault's case, its 3.5 km wide body has been spinning faster over time and now completes one rotation every 2 hours, the upper limit of what an asteroid can endure. This rapid rotation generates centrifugal forces that are stronger than the asteroid's gravity, causing loose material to be ejected into space. These ejections form the tails, and over time Gault will likely disintegrate entirely. Like many other asteroids and comets, Gault isn't a solid rock, but a fragile rubble pile held together by weak gravitational forces. The asteroid belt, with its chaotic population of 1 to 2 million asteroids larger than a kilometer and countless smaller ones, is a dynamic region. To illustrate this, let's examine P/2010A2. At first glance, it appears to be a typical comet. However, a closer look at its nucleus reveals an unusual filamentary structure. Surprisingly, this is not the comet's nucleus. It isn't even a comet. A collision between two asteroids is an extraordinarily rare and dramatic event in our solar system. Unlike planets and moons, which have largely settled into stable orbits, asteroids remain in a chaotic environment where occasional impacts still occur. These collisions are difficult to observe in real time, making each recorded instance an invaluable opportunity for scientists to study the physics of such events and their impact on the evolution of our solar system. What we're witnessing in this case is the aftermath of one such collision, marked by an unusual X-shaped structure near the nucleus. This striking formation consists of debris from the impact, with fragments of rock and dust scattering in multiple directions. The collision itself would have been a violent, high-speed event likely occurring at tens of thousands of kilometers per hour, far faster than any collision on Earth. At such extreme speeds, even a relatively small impact can unleash tremendous amounts of energy, shattering solid rock and dispersing it across space. As a result of the impact, the ejected material does not simply disperse evenly, but follows complex gravitational and momentum-driven patterns. Some of the debris is thrown outward in 4 distinct directions, forming the characteristic X-shaped pattern seen in Hubble's images. This unusual configuration arises from the way the two colliding bodies fragmented upon impact, with some of the material moving at different velocities and angles depending on the force of the collision and the structure of the original asteroids. Over time, the gravitational pull of the remaining asteroid mass attempts to draw some of this ejected material back toward the center of mass. However, not all of it is recaptured. While some debris may eventually settle back onto the asteroid's surface, other fragments gain enough velocity to escape entirely. These free-floating particles drift away, forming a faint tail similar to that of a comet. Unlike a typical comet's tail, which is driven by solar radiation and gas sublimation, this tail consists purely of collision-generated debris, marking the event as an asteroid impact rather than an icy cometary outburst. Observing such a collision provides crucial insight into how asteroids break apart, form rubble piles, and contribute to the ever-changing landscape of our solar system. These events help shape planetary systems and may even play a role in delivering materials necessary for planetary formation and evolution. Despite the occasional chaos, most asteroids in the belt follow relatively stable circular orbits around the Sun. But if an asteroid strays too far from this path, as comets do, it risks encountering a far more powerful gravitational force, Jupiter. Often called the solar system's vacuum cleaner, Jupiter is a dominant force in this region. Its immense mass accounts for nearly 3/4 of all the matter in the solar system outside the Sun, giving it a gravitational influence that shapes the fate of nearby objects. A striking example of this occurred in 1994, when the 2 km-wide comet Shoemaker-Levy 9 ventured too close to Jupiter. The planet's gravity not only captured the comet but also tore it apart, breaking it into several fragments. By the time the fragments impacted Jupiter, they were already scattered, marking the first ever direct observation of an extraterrestrial collision. Interestingly, Shoemaker-Levy 9 had been captured by Jupiter roughly 2 decades earlier and orbited as an active comet, a phenomenon also observed for the first time. However, its orbit eventually brought it perilously close to Jupiter's surface. The resulting tidal forces shredded the comet, and just a year later, its fragments collided with Jupiter at an astonishing speed of 60 kilometers per second, over 210,000 kilometers per hour. The impacts on Jupiter generated fireballs reaching temperatures of over 23,000 degrees Celsius, soaring an astonishing 3,000 kilometers above the planet. The most significant impact left a dark spot spanning 12,000 kilometers, roughly the size of Earth, and unleashed energy equivalent to 6 million megatons of TNT, more than 600 times the power of the world's combined nuclear arsenal. While other impacts have been less dramatic, they have been observed and photographed, lending credibility to the theory that Jupiter acts as a cosmic vacuum cleaner, shielding the inner planets of the solar system from catastrophic collisions.